Hey kids! Today we're gonna talk about uniforms! Yeah. So, our shaders are pretty boring right now, I would say. Like, they're quite static, nothing moves. Like, if we want to move our quad or change the color or something, how do we do that? Well, we can move it by changing the vertices. That we can do. But not only is it slow, it's also, quite annoying to have to, change vertices and, upload those and stuff like that every time we want to move something. So rather, it would be nice if we could change, somehow set parameters in the shader. Like, maybe the color output right now, it would be cool if that was a parameter we could set through code somehow. And that is exactly what uniforms are. So first of all, let's go into our shader and create a uniform that we can later change. So the way you do that is to use type uniform in global space. Usually I do those at the top, but it doesn't matter. Uniform, and then we gotta specify which type it is. So if you want to do a color, then that would be a wec4. So we want to do a wec4 uniform. And then we set the name. And I usually do u underscore as a naming convention. Again, it doesn't matter. Feel free to name it, come up with any naming convention that you like, but I like the u underscore. And we call that color. Yeah, let's just call it color. Hopefully it doesn't become too confusing that it's u and o color, but that's what I'm going to do. And so I will replace this hard-coded color with this our new u color. And let's see what happens. Okay, cool. So we didn't get a compile error, so that's good for our shader, that is. It's black now, so all uniforms by default are zeroed. So we have our uniform, our parameter, but it's just that it's all zeros at the moment. So let's change that. Excuse me. So first, like everything else in OpenGL, we have to receive a handle to our uniform. So we will use the function called gl get uniform location. So the gl get uniform location, it takes a program. So that's the shader program we want to get the uniform from. So in this case, it doesn't matter if it's the vertex or the fragment shader. Which one doesn't matter. It's just the program that matters. And then we pass in a name, and that's just like, what's the name of the parameter in code. So first of all, we'll feed in our program here. Oops. And then we'll give the name as just a string. So we'll do u underscore color. All right. And what does that return? It returns a, well, that doesn't help. It returns a gl int. All right. And that's gonna be the handle to our uniform. So I'll save it, gl int, and usually I like to call those the same as the uniform like that. I know it breaks naming convention, but I actually think that's fine. It becomes then very clear that this is a uniform handle and not something else. But you can call it color uniform or anything like that if you want to. I like to have this naming convention, but cool. So now we have a handle to our parameter in the shader. Let's set it to some cool value that's not just completely black. So with that, I'll do gl uniform. And already there's like a bunch of these uniform functions. So the naming convention is quite what am I looking for? It's quite there is a naming convention. I don't know. I spoke myself into a hole I did not get out of. So okay, so let's write this down. Whoa. Whoops. Oh no, that's not. Get away. Get away. Okay. Uniform. That my pad is like super fast today. Oh no, the settings have been reset. That's why it's so fast. Hold on, let me just go in. Bamboo. Let me just Sorry guys, I'm just gonna do this real quick. Pentile, advanced, no. Mapping, there we go. Monitor 2, okay, cool. Okay, there we go. There we go, now it feels good. Okay, sorry about that. Right, so uniform. Uniform names. Alright, so it always starts with GL uniform. Oops. Uniform. Then there's a number, so I'm going to call it N. And that's how many components this uniform has. So in our case, it's going to be 4, because it's a vector 4. Alright. Then it's the type. So I'll do type. In this case, I think it's D is integer, and U is, I think, uint. I'm not too sure though, honestly. F is float. And I think those are the main ones. I actually don't remember anymore, but so, and then it's let's do. Then it's V. I'm gonna do a question mark there. So the V is optional, and what the V does is, are you passing this in as a pointer to the data? And that might seem very confusing right now, but let's actually show it, and then maybe it'll make a little bit more sense. So I'll do 4F, and here you can see it's either 4F or it's 4FV, and let's do 4F for now. And you can see that function takes the location, and that's the handle to our uniform. So I'm just going to type in uColor. And then it just gives us, oh, here's 4 floats. So I'll just do, which color should we do? Chat. Let's do 0.2, 0.5, and then 1 maybe. So I don't know what color that's going to be. And then just 1 for the alpha channel. And let's see what happens. Hooray! There it is. So that's our uniform. It actually looks very similar to before. Let's do red instead. So I'll do 1 here. And then let's do 0 for blue. There we go. So we're back to our orange color. All right. So what's the difference between that and the V version? So if I do FV, let me check that out. Okay. So it's still the handle. So that's the handle to the shader. Then it's count. Okay, that's interesting. And then it takes a floating pointer. So what this means is that you can pass in a pointer to a floating point array. So let's do that. Let's just comment this out for a while, and we'll do float. That's how we do arrays. Float my color, and that's going to be equal to let's do like this. All right, so that's our floating point array, and we'll do uColor. And the count is how many, that's not how many floats there are. This is if you're doing a uniform array, all right? So if you're doing a uniform like this, for example, that means it's an array of 5 vector 4s. That's the uniform. So to pass that in, you would have an array in code that's 5 times 4, so it would be like 4 more of these, 4 more colors like this, and then you will pass 5. That's the count of how many vector 4s, and then the pointer to your color, or the pointer to your array. But in this case, we only have 1. We don't do arrays right now. We'll do it later. And like so, I just want to show you that this also works just fine. And there we go. Now we have some sort of magenta color. So you can either define an array and just pass that in as a pointer, or you can use like hard coded into the function call. And sometimes one is more convenient than the other. But they're just 2 different ways of doing it. And of course, if you have an array as like a uniform array, then you have no choice. You have to use the pointer version, because that's the only one that has like the count argument. All right. But for your single variables, then you can do either or, either the 4f or the 4fv. Great. All right. Quite easy. So, but again, it's quite static. You know, it's still like, I mean, how is this better? We're just like, you know, now we can set in code which color you want. But of course, the good thing about uniforms is that you can change them in runtime. You can change them as much as you want. So let's do that. Let's do some cool stuff. So let's get the time. I gotta actually Google. I don't know GLFW getting time, so let's check it out together. I could probably just type something, but it's better to just go in. Maybe this. This doesn't help me. Let's search the time. What? Okay. You win. I'll Google it. GLFW time. Time input. Yeah, sure. Okay, here we go. GLFW get time. Returns the value of the GLFW timer. Okay, what unit is it? Function returns the value of the GLFW timer unless... okay. The current value in seconds. Okay, cool. So this gives us time in seconds. So that's very helpful. So I'll save it here. Float time is equal to GLFW get time. Does that compile? Sure does. So what should we do? Let's do something fun. Let's do so let's do GL uniform 4F. So I'll do the color, and then let's do a sin available. Hopefully, let's say sin of time 0, and then the cosine of time. Let's see what that looks like. Oops, they're not here, so let's include math. Okay. So I'm passing in as R, I'm passing in the sine of time, and then for green I'm passing in 0, blue I'm passing in the cosine of time, and then 1. Let's see what happens. All right, so it's doing something. Like if sometimes it's black when both the sine and the cosine is negative, but we can at least see some change. So you know that makes me happy. That's quite cool. So so great. So maybe we can just pass time into this shader. And then we can maybe do some wacky stuff and try to really get things going. So I'm actually gonna, in the vertex shader, I'm gonna define a uniform float. I'm gonna do u time, like so. And let's just do it. Let's just pass it in as first. So I'm gonna actually get rid of this for now. And also I'm gonna do the clear color as just gray instead of doing this annoying blue color. Yeah, that's much better. It's much easier to see now. So I'm gonna get time here. So I'm gonna do GL int u time, GL get uniform location, program u time. Again, it doesn't matter if I'm getting from the vertex or the fragment shader. All that matters is the program, and it will actually get them from both. Okay, so now we have a handle to the time uniform, and I'm gonna set that here. So we'll do GL set uniform 1F. So do time and then time. This is actually the first time I failed my naming convention. There we go. Oh, excuse me. Okay, so now we have time in the uniform, but we're not using it for anything. So let's use it to move this quad around, shall we? That seems like a good thing to do. So I'm actually gonna let's do GL position x plus equals the sine of time. All right, let's see what happens. So if I restart, nice, there we go. Now it's moving back and forth. Actually, now I'm seeing I have VSync on this. That annoys me. But so what's happening here? What are we doing? Let's just like look at what the code is doing here. So we're setting GL position. So that's a vec4. So we're setting GL position to be the vertices of the quad. And then we're adding the sign of u time to the x. To the x component, I should say, of the position. So just as a reminder what sine is, if we go into Desmos, I highly recommend Desmos. It's a really good graphing calculator. Here we go. If I just type in sine of x here, it's just a wave function, all right? So it starts at 0, it goes up to 1, and then it goes down and down to -1, and then goes up again to 1, and then down to -1. So it just flip-flops between -1 and 1, back and forth like that. And we're just adding that to each vertex, all right? So that means, because u time is going to be the same for every vertex, right? So u time is exactly the same throughout all of the shader passes for every vertex, for every pixel. All the uniforms are always exactly the same value. So the sine of u time is also going to be the same value at every vertex. So that means we're going to add, so like now we're adding -1, then it goes up. Now we're adding +1 to every vertex, and then it goes down, passes 0, and then -1. So we're just moving the mesh back and forth like that. But let's do something a little bit more interesting. What if I do sine of u time times GL position? Whoops. Y. I've gone crazy. Try to visualize in your head. Like, do sort of the calculation in your head. Like, okay, what does this mean for, let's say the top right vertex? Okay, what's the y component gonna be? And if sine of u time is 1, what is that gonna be when you times it by the vertex y? And the same thing for all the quadrants. Try to sort of visualize in your head kind of what's gonna happen. Or you can just not do that and just run it, and you can see that we're sharing the mesh now, because now we're not transforming each of the vertices equally anymore. We're not applying the same offset to all the vertices. Rather, the ones on the top have a y component of 0.5. Both of the vertices on top has a y component of 0.5. That means the sign is going to get halved, right? So it's still going to go from 1 to -1, but it's going to get halved because we're timesing it by 0.5. So instead it's going to go from 0.5 to -0.5 to 0.5 to -0.5. But for the ones down below, they're -0.5 in the y component. And that means, okay, it does get halved, but it also gets flipped, right? Because if you time something by a negative number, it goes from a positive to a negative number, or if it is a negative number, it goes from a negative to a positive number. So you're flipping the sign of the number, is what we call that. So instead of going 1 to -1, it goes from -0.5 to +0.5 in reverse. So when the sign is positive, the output is going to be negative, right? So if the sign is 1, then the vertex is going to offset by -0.5. And when the sign is -1, the vertices are going to be offset by positive 0.5. And that's why we get the shearing effect, because while the top is moving to the right, the bottom is moving to the left, and then so on. But important to note that the triangle is still solid. Like, it's not like just the corners move away and the middle is still is flat. The triangle is defined by the vertex shader. So if the vertex shader is moving the vertices around, that will affect the whole triangle. Like, the surface will still get filled in between those two vertices. It doesn't matter how much you're transforming them. Cool. So let's do one final thing that I think is pretty fun. Oh no, actually before that, no, let's not do that. Let's do something in the fragment shader first. So I'm gonna define the time uniform in the fragment shader as well, which is fine. These two will actually refer to the same value. So when I'm getting the uniform handle in code, I'm gonna be referencing both of those uniforms at the same time. Instead of this hue color, I'm not gonna use that anymore. I'm actually gonna define two colors here. So let's define let's do color A, and that's gonna be equal to let's do so bad with colors. Let's do yeah, that's good. I'm thinking like writing the same two colors over and over again. Let's do a green one. I haven't done a green one yet, so let's do 0.1 and then just 0.9 and then 0.3. Yeah, that's that. And I want this to flip back and forth, right? So I want it to fade from A and then to B and then back to A and then back to B. So how do we do that? You might know about the lerp and the lerp, or the linear interpolation. If I write that, lerp, that will take two values. So we're going to do color A and color B. It doesn't matter what the type is. Or in this case, it doesn't matter. So we're giving two values. We're giving A and B. And the lerp interpolates between those two values linearly. That's why it's called linear interpolation. And it takes an alpha, that's what it usually is what it's called, which is a scalar, a number, that goes from 0 to 1. Where if it's 0, then the lerp interpolation returns color A. And if it's 1, then the linear interpolation returns B. So those are the two edges, right? But then as you go towards the middle, it's gonna blend those two values. So as you're going from 0 upwards, it's gonna start interpolating towards B. So if you're at 0.5, you're gonna get exactly the halfway point between A and B. And then as you're moving past the halfway point, it's gonna become more B, until you reach 1, at which case it will just return B. So it will blend between those two. Again, a value between 0 and 1. So I'm just going to type in 0, the sign of U time here. So I'm going to use the sign, which is goes back and forth in a wave. And I'm going to use that as the alpha. And hopefully that will give us, A, and then it's going to transition to B, and then it's going to go back to A, and then it's going to go back up to B again in a nice blendy way. So let's see what happens. Oh. That looks pretty good. So if it's white, that usually means we have an error. Oh, you're right. OpenGL does not find a global functional lerp. Right, okay. So I asked you might know about lerp. Well, it's not fucking called lerp in OpenGL for some reason, or GLSL, sorry. It's called mix. All right. I don't know. Hooray. So now, one thing I'm noticing here, might not be super obvious, but this color here is pink. And I know that pink is fully red and fully blue. While the color I specified here is not fully red and fully blue, it should be more blue than it is. This is way more pink than it should be. And that's because sine, again, if we look at the graph, sine goes from 0 to 1 to -1, all right? And I just told you that the linear interpolation function expects an input between 0 and 1, all right? So what happens if you go further than that? What happens if you go past 0 and then go to -1? Well, it's kind of complicated, or not complicated, but it just sort of continues the pattern, right? So it's gonna interpolate towards A, and you know the interpolation formula is just gonna continue, which means that it will just kind of it gets weird. Like there's no easy analogy to explain exactly why we're getting what we're getting, but that's the bug. And unfortunately, it's quite easy to fix, because what I want to use. I mean, the easy way is to just clamp it, right? To just be like, okay, I'm just gonna lop off this bottom bit, but it's gonna be quite boring because it's gonna go like from 0 to 1 to 0, and it's gonna be like flat 0 for quite a long while, and then go back up to 1, and then down 0, and then flat 0. I want actually to squish this sine wave up. I want to squish it up so it goes between 1 and 0 instead of 1 and negative 1, and it's quite easy to do that. You just do times 0.5, which will squish it down. You know, so it goes from 0.5 down to negative 0.5, so we squished it down a little bit. And now we want to move it upwards, all right? So we squished it, and now we want to move it upwards. So I'll just do plus 0.5. So now I've squished it and then moved it. So now it goes between a nice 1 and 0, all right? 1 and 0. With still the same period. So I'll use that. Times 0.5 plus 0.5. Let's see what happens now. All right, there we go. So now it doesn't go to hot pink anymore. It goes to a more magenta blue color. So that's what we expect. Cool. Let's do one more thing before I call it quits on this one. This is usually what I like doing because I just think it looks very pretty. Let's make this man spin. Do I swear? I usually swear, right? It's okay to swear. Poo poo. There we go. I swear. So we wanted to rotate, and there's a formula for that. I won't go into the formula because it's not really important. But it looks like this. Let's save it into a variable first to make things a little bit more easy. So I'm going to say vec2 pos is equal to a position. And no, I'm not going to do that. Never mind. I'm going to do pos.x is equal to the a position that y times, let's see here, it's the sine of u time plus minus a position x no, this is wrong. No, I fucked it up. It's a position, the x times the cosine of u time, there we go, minus a position y times the sine of u time. Okay, and then we'll do pos y is equal to a position y times the cosine of u time plus the a position times sine of the u time. All right. So there we go. Quite a complicated formula, but it's fine. So we're taking these two are just so x is equal to x times the cosine of time, and y is equal to y times the cosine of time. All right, and this means that if u time is 0, so if we have 0 rotation, cosine will be 1 and sine will be 0. So we can sort of ignore these two last terms, all right? It's okay if you don't understand this completely. I'm just kind of going through it. We'll be doing more of this later on. It's sort of our introduction to the trigonometric functions, because they're very important in 3D mathematics. So if the u time is 0, then cosine will be 1 and the sine will be 0. So that means this is the only thing that actually matters. So it would just be x is equal to a position x times 1. So that's just a position x. And then y will be a position y times 1. So that's just y. Makes sense. And then it's going to rotate around. I'm just going to bring those two up, actually. Let's do sine of x and then cosine of x here. Whoops. That's two waves. So you can see they sort of go in and out of each other. So when one of them is 1, so this is when a cosine is 1 at 0, then the sine is 0. All right. So when one of them is 1, the other one is always 0. And when one of them is minus 1, the other one is also 0. So, you know, they grow and shrink sort of in tandem like this. All right. So at 0 angles, cosine is 1. Great. Fantastic. And then it goes up. And here's, you know, pi divided by 2, but you can see that as 90 degrees. I'm just going to say that's 90 degrees in radians. Now the sine is 1 and the cosine is 0. So what's going to happen then? Well, then this part is going to disappear. So this cosine is going to be 0. So this part is not going to be there anymore. And what are these two going to be then? So x is going to become, okay, minus a position y times the sine of u time. Okay, so that's 1. So I can just say the position x will become minus a position y. Okay. So let's just think about that a little bit. So x is top right. And it will become, and the x will become minus y. So y is 0.5, so x will become minus 0.5. And what will have happened is that it will have rotated 90 degrees to the left, counterclockwise. And the same logic will apply to this pos.y, position.y, is plus a position x times the sine of time. I implore you to sort of think about this a little bit more. It's hard if you don't have a very intuitive understanding for the cosine and sinus function. That's fine. I don't know if you've had the 3D mathematics course yet. I know I held that for the last year, the year before you guys, and there, like, the big portion of the time I was talking about vectors and sinus and cosinus, because I think those two concepts are like the most important in game development. Sinus and cosinus are incredibly useful. Once you learn about them, you will find uses for them everywhere. But yeah, so this is the algorithm for rotating something about a plane. All right, this, like, you know, x times cosine minus y times sine, and then y times cosine plus x plus sine. That's the general formula for rotating a point. Not super important to remember. I sort of have it in my brain. I just want to get you guys sort of familiar with this type of mathematics, because we're gonna be doing a lot more of it. So it's okay if it doesn't make total sense. That's totally fine. See this as just sort of like I'm showing you what it can look like, what mathematics could look like. But then later on, we're gonna go into way more detail, and I'm gonna explain it way more better than I did now when I'm tired. So let's just do that then. So let's just pop this pos into x and y component of the actual final GL position, and let's see what happens. Hooray! It's spinning. Great. All right. It kind of grew very quickly. I'm sorry if it became like very complicated very fast, but that's fine. That's gonna be this course. I'm gonna warn you right now. This course is gonna get very complicated very fast very soon. So I think next week, when we're gonna start talking about, you know, matrices and spaces and projection and stuff like that, get ready to get your brain fried. So I think I'm gonna do less lessons per day next week, just to let you guys sort of sink in with the mathematics and sort of try to visualize what's sort of happening. Cool. I think that's gonna be it for uniforms. The most important takeaways from this is moving vertices in the vertex shader is very important, all right? That's a very big takeaway that I want you guys to remember. And how uniforms are shareable between the vertex and the fragment shader. Yeah, I think those are the biggest takeaways, actually. So yeah, I'll see you guys next video.